Hi, my name is Chris Wheeler. I'm a master's student at Georgia State University. My advisor is Dr. Sarah H. Ledford, and this is a presentation on my research regarding the relationship between urban land use variation and base and stormflow water quality in the South River Watershed, which is a highly urbanized catchment in Atlanta. Before I talk about my research in particular, I want to give a brief introduction to the idea of systemic stream degradation, especially previous work performed in the Atlanta area. Following the worldwide trend of urbanization, the Atlanta metropolitan region, which consists of 10 counties, has experienced a nearly 100% growth in population from 1970 to 1995. And this growth has caused significant ecological stress to the environment via rapid increases in residential and industrial development, as well as the magnitude of impervious surface coverage, or ISC. This high level of urban development is compounded by Atlanta's early history of installing combined sewer overflows, or CSOs, for stormwater control and management, instead of entirely separate systems for sewer and stormwater control. In Atlanta, multiple studies already have been performed that confirm the presence of these typical stream impacts associated with urbanization, including changes in baseflow, stream solutes, and stormflow. For example, in the upper Chattahoochee River Basin, watersheds across a range of urban development showed significant increases in baseflow concentrations with increasing levels of urbanization. Additionally, baseflow concentrations were significantly higher for any level of urbanization when compared to the rural sites in the study. In addition to elevated solute concentrations, urbanization in the Atlanta area has led to dramatic alteration of natural flow regimes. A 2001 study showed the highly urbanized Peachtree Creek exhibited peak flows 30 to 100% larger than the comparison forested sites, consistent with other comparative watershed studies in the area. Stream discharge at Peachtree Creek also decreased much more rapidly after storm events, as quantified by storm recession constants that were significantly greater than other sites. So this indicates that urbanization has caused an increase in hydrograph flashiness for Peachtree Creek as expected. So next, I would like to speak generally about concentration discharge, or CQ relationships in hydrology. Such relationships have been studied extensively at multiple spatial and temporal scales. So in general, CQ relationships at any scale can be placed into three distinct categories: flushing, dilution, or chemostasis. Flushing behavior suggests that the chemical constituents are transport limited in the watershed, meaning that there is an excess volume of solutes within the watershed and the amount lost to runoff is controlled by the magnitude of discharge. In other words, in a flushing system, as discharge increases, so does concentration. In contrast, dilution behavior suggests that the system is source limited, meaning that increased discharge simply dilutes the concentrations observed at baseflow. Or in other words, as discharge increases, concentration decreases. Finally, a chemostatic system is one in which concentrations remain constant regardless of discharge magnitude. As you can imagine, the character of these relationships varies depending on the scale of measurement and many other characteristics of the system that you're studying. Recently, key work has shown that on multi-year and even storm event timescales, many CQ patterns are essentially chemostatic. However, examining CQ relationships on a storm event scale can nonetheless provide crucial information, particularly in a localized remediation context. So if you look to the right of this slide, here's a long-term CQ graph using almost 10,000 15-minute scale observations from summer of 2020, taken at a USGS gauge located on the South River at Flakes Mill Road. This USGS gauge represented the outlet site for our study, and we used it to define the extent of the South River watershed. As such, an important part of our study was storm event sampling in an effort to characterize typical storm event CQ responses in our study watershed. So-called hysteresis loops were created for all applicable storm events during summer 2020, where discharge in cubic feet per second is plotted on the x-axis, and solutes, including specific conductivity, nitrate, and chloride, be plotted on the y-axis. These loops are then analyzed with respect to their size, shape, and rotational pattern. The size of the loops is indicative of the magnitude of the response of the solute to discharge relative to its baseflow value. The general shape and orientation of a loop on the plot suggests whether major ion and nutrient concentrations exhibit flushing or dilution behavior during the storm event in question. Finally, examination of the rotational pattern of the loop, that is clockwise or anticlockwise, will reveal whether the measured solute peaks on the rising or falling limb of the hydrograph. Thus, a clockwise rotation suggests that the constituents driving specific conductants or any solute are located proximal to the stream, while an anti-clockwise rotation suggests that the constituents are located further from the stream. So, as is apparent, looking at event scale hysteresis loops can provide insights on catchment scale, mobilization, and transport processes. That brings us fully to the objectives of this study. First, we want to characterize variation in baseflow hydrochemistry in the headwater streams of the South River Watershed, and then relate this to differences in land use and other characteristics. So why the emphasis on urban headwaters? Well, previous work has consistently demonstrated the outsized influence of headwaters to the ecological health and water quality of a stream network at large. In particular, the Lodic inter-site nitrogen experiment, or LINX, nutrient addition studies have provided crucial evidence of the integral role that small streams play in nutrient dynamics on larger spatial scales. Regarding the second objective of this study, we wanted to examine relationships between stream discharge, or Q, and concentration, C, of various solutes during storm events for reasons outlined in the previous slides. Now to a more complete description of our study site that I've been referring to. The South River Watershed is located in the southeastern portion of the metro Atlanta area, principally in DeKalb County. DeKalb County has a total population of almost 760,000 people, according to the 2016 census, and encompasses an area of approximately 694 kilometers squared. As with the Georgia Piedmont generally, most soils are residuals, most notably the distinct red clay soils of the Cecil series, formed via weathering of underlying granite, mica schist, gneiss, and hornblende schist. However, continuous urbanization since the late 19th century has dramatically altered the landscape and hydrology of the entire metro Atlanta region, including the South River Watershed, especially in terms of impervious surface coverage. As we can see from the tables to the right of this slide, the entire drainage area of our study site is characterized by a total urban, meaning total impervious, land use coverage of 73.6%. Moving on to sampling methods for our study, regular baseflow sampling was performed from June through September 2020. Water quality samples were collected 15 times from a total of 18 sites in the South River Watershed. 3 of these sites were co-located with USGS stream gages. These 18 baseflow sampling sites were collected in an attempt to adequately characterize the headwaters of the South River Watershed, that is, locations representative of the most upstream reaches of first-order tributaries in the basin. However, due to site access limitations, sample sites were ultimately placed at the most proximal public cross street to the actual headwater locations. Samples were collected from each site using 2 60 milliliter HDPE bottles and rinsed 3 times with stream water prior to collection. Samples were filtered using a 0.45 micrometer pore size paper filters and stored at 4 degrees Celsius prior to analysis. So the figure that we see to our left is an outline of the aerial extent of the South River Watershed with all 18 baseflow sampling sites marked as circles. The 3 red circles represent sites where storm event sampling was also performed. The right figure on this slide shows precipitation in millimeters per day for the entire duration of the baseflow sampling campaign. Red dots mark days where baseflow sampling was performed. So, as previously stated, in addition to baseflow sampling, storm event sampling was performed during summer 2020. Time series concentrations were quantified at 3 USGS gauges for 13 discrete storm events, June through September 2020. Temporal resolution varied between storms due to equipment limitations. Through the selection of USGS gauges at sample points, 15-minute discharge and specific conductivity measurements were also available for use in CQ analysis. Regarding chemical analysis of both Baseflow and Stormflow samples, field parameters were measured and recorded in situ at each Baseflow sample site. So after the collection of our storm event data, we created CQ loops for 3 parameters: specific conductivity, nitrogen, and chloride, and calculated 2 normalized indices for interstorm and intersite comparison of the CQ responses. First, to calculate the hysteresis index, discharge and concentration must first be normalized to a 0 to 1 scale. After normalization, the hysteresis index is calculated by subtracting concentration values on the falling limb of the hydrograph at a given discharge from those on the rising limb at the same discharge value. As such, values of this hysteresis index will fall between -1 and 1. Positive values represent clockwise rotation, and negative values represent anticlockwise rotation. The magnitude of the value represents the size of the area inside the loop, which is in turn representative of the relative magnitude of the hysteretic response. Another advantage of this index is that it can be calculated at different levels of resolution. So the user can choose to calculate HI at any increment of discharge. For this study, a script was executed in R that calculated the HI at 2% increments of discharge, giving 50 separate HI values that were averaged to yield the final value. In addition to hysteresis index, a normalized flushing index was also calculated according to the previous methodology. Positive values of the FI represent a flushing response, while negative values represent a dilution response. Moreover, like the hysteresis index, the magnitude of the flushing index represents the relative magnitude of the flushing or dilution response. Using these 2 indices and plotting the results on a scatter plot provides a more robust method to compare CQ responses among and between storms, sites, and solutes, thereby more easily parsing mobilization and transport mechanisms for various solutes on the watershed scale. So first, I want to look at the Baseflow hydrochemistry results. So looking at the top right, here's a box plot for nitrogen at all of our Baseflow sites. Most sites exhibited relatively little variability temporally. However, as you can see, there are certainly a few exceptions. Of the sites on the high concentration end of the spectrum, BS18 exhibits a much higher median nitrogen and chloride concentrations than any other sites, as well as a much higher variability. So looking more into BS18, this is an example of one of the many suspected outfall events at the Custer Street CSO, which is about 2 miles upstream from where we were sampling at BS18. So as you can see, between about 5 and 17 hours, you have this plateau in discharge, which is in red, which is representative of the CSO release event. Now here are some comparisons between hydrochemical concentrations and land use characteristics, namely total urban and total forested land use in each watershed, compared with mean concentrations associated with Baseflow sites. As shown by bolded p-values in the table, we found 3 statistically significant regressions, 2 which are shown in the scatter plots to the right. Although the R-squared values on these relationships are low, it's reasonable to assume that total urban land use on the watershed scale is one of the factors controlling mean nitrate concentrations at these sites. In addition to the analysis of land use and land cover in relation to Baseflow, we also use a technique called principal component analysis to reduce the dimensionality of our Baseflow dataset by forming linear combinations of potential explanatory variables from 11 original variables measured at Baseflow, including both the chemical data and field parameters. The use of PCA is popular with multivariate environmental data sets. PCA can help parse driving trends in a data set, as well as more clearly show groupings of observations with similar combined characteristics, that is, principal components. Results of the PCA showed a clear distinction between the first two principal components that were generated, PC1 and PC2. PC1 represents a groundwater signal, that is sodium, sulfate, chloride, calcium, and specific conductivity, while PC2 represents an in-stream metabolism signal, that is nitrate, dissolved oxygen, and temperature. So the graph you see on this slide is a scatter plot with PC1 plotted on the x-axis and PC2 plotted on the y-axis, and 95% confidence ellipses were drawn around the samples from each site. So looking at the orientation of these ellipses, you can see that two of the sites have a distinct orientation from the rest. These are sites 12 and 16, which are the inflow and outflow to a small residential pond, respectively. Now I want to move on to the results of the stormflow component of our study. So here are some hysteresis loops that we generated from storm events that we captured. The two plots on the right represent the typical response that we observed in this study. Namely, the hysteresis loops exhibit a negative slope, signifying dilution, as well as a clockwise rotational pattern. In contrast, the top left plot shows an anomalous positive slope for nitrate, indicating flushing for that particular storm event. So here are the plots of the normalized flushing and hysteresis indices for each storm for both nitrate and chloride, with dots on a color gradient representing 72-hour antecedent precipitation magnitude. As you can see, both plots show that the majority of storms fell in the top left quadrant, representing a dilutive response with clockwise rotation. While all storms fell into this quadrant for chloride, there are a few storms that showed flushing for nitrate. Of these, the storm with the largest nitrate flushing response is also the storm with, by far, the highest 72-hour antecedent precipitation. So I would like to conclude with a few key takeaways from this work on the South River Watershed. So first, although we haven't yet parsed all the controlling factors for concentrations in this system, it's clear that at least for nitrate, urban land use on the watershed scale is correlated with the magnitude of nitrate concentrations observed at each site. Furthermore, the results of principal component analysis showed the presence of two distinct chemical signatures represented by PC1 and PC2, which were groundwater driven and metabolism driven, respectively. Furthermore, the results from our storm event study were remarkably consistent, with most sites exhibiting dilutive behavior and clockwise rotation for chloride, nitrate, and specific conductivity. However, the anomalous nitrate flushing that we observed is likely driven by antecedent precipitation, given that the storm exhibiting substantial N flushing also had the largest antecedent precipitation by far. So taking all this evidence together, both the baseflow and stormflow components of this study, we can conclude that the South River Watershed is likely a source-limited system, and that groundwater represents the highest concentration component of stormflow, which is generally always diluted by lower concentration of precipitation during storm events. This type of localized info on watershed transport and mobilization processes for solutes could certainly be useful for future remediation efforts.